0-day brief.
I want you to imagine something just for a second. Read this quote from our briefing today and let it really sink in. Quote, "If someone cracks Nginx, they're not defacing your homepage. They're standing in your hallway with a key to every door."
Yeah, that paints a dramatically different picture than the usual scenario we hear about, right?
Absolutely.
Where an attacker just, changes the text on a public-facing website to cause some temporary embarrassment.
Right, like a digital prank. But today, our mission is unpacking exactly how someone gets into that internal hallway. We are looking at CVE 2026-42945.
Which is a huge deal.
It is. It's a newly disclosed, highly critical vulnerability in Nginx. And we have a really robust stack of sources for this deep dive today. We're looking at vulnerability briefings, official security advisories from F5 and the Elm Linux maintainers, plus active threat intelligence data. And that is current as of today, May 21st, 2026.
It's all happening very fast.
So fast. Okay, let's unpack this. Because Nginx is, well, it's basically a cornerstone of the modern internet. You interact with it every single day, whether you realize it or not.
Yeah, it sits in front of millions of the websites and apps you use.
Exactly.
And to ground our conversation right out of the gate here, we are not merely looking at a standard software bug today.
No, definitely not.
We are looking at an 18-year-old structural fracture in the foundation of the web. This vulnerability, it fundamentally alters how we view network security and the assumptions we make about the safe middleman architecture we all rely on.
The sheer age of this flaw is just astonishing to me. According to the timeline in our briefings, this bug was introduced in 2008.
2008?
Yeah. Specifically, it entered the codebase in Nginx version 0.6.27, and it has survived every single security audit, every automated code review, every update, all the way up until the current version, 1.30.0.
I mean, we are talking about a piece of code written before the mainstream adoption of cloud computing.
It predates the iPhone 3G.
It does. And to understand how it stayed entirely hidden for nearly 2 decades and how an attacker actually exploits it, we have to look closely at the underlying mechanics.
Right, because it's pretty technical under the hood.
It is. But the briefings provided a really helpful analogy to visualize this without, getting bogged down in reading raw C code. Imagine Nginx is a massive, incredibly busy post office facility.
Okay, so millions of letters are arriving every second, and the facility's only job is to route them to the correct internal departments.
Exactly. Now, inside this post office, the clerks use a tool called the rewrite directive.
The rewrite directive, right.
Think of this as a blank routing slip. A postal clerk looks at an incoming envelope, copies a specific part of the original address onto a new slip, and writes a completely new destination for it.
Okay.
For example, if the incoming zip code says 90210, stick a new slip on it and route it to the Beverly Hills processing bin. It's a fundamental routing mechanism.
But things get a lot more complex when those postal clerks start handing these routing slips off to other clerks down the line.
Right, and that process is called chaining routing slips. The first clerk writes a slip, hands the letter to a second clerk.
And a second clerk reads it.
Yeah, that second clerk reads the newly attached slip, evaluates it, and potentially writes another entirely new slip based on that secondhand information.
So in the context of Nginx, this translates to chaining directives together in the configuration file.
Exactly.
Like a rewrite rule pointing to another rewrite, or an if statement, or a set command. Decisions are being made sequentially based on modified data.
Yes, and the sources specifically highlight something called PCRE captures being involved in this chain.
Right, those are the variables you might see in a config file, like $1 or $2.
Yep. PCRE stands for Perl Compatible Regular Expressions. In our post office analogy, using a PCRE capture is like the clerk taking a highlighter, highlighting a highly specific segment of the original address.
Like perhaps just the street name.
Exactly, just the street name, and explicitly copying only that exact highlighted text onto the new routing slip.
Honestly, that sounds like a totally standard feature. But then the source material introduces the trigger for the vulnerability, which is just a simple question mark character placed inside the replacement string.
Yeah, the question mark is where the internal logic of the system completely desynchronizes.
Wait, just one question mark?
Just one. To explain why this breaks the software, we have to talk about how the C programming language handles memory. In C, developers have to manually tell the computer exactly how much memory a string of text will need before they actually build that string.
Right.
It's a 2-pass system.
So pass 1 is calculating the size of the box you need.
Correct.
And pass 2 is actually packing the box with the text.
That is the core of the issue. During Pass 1, the Nginx rewrite module evaluates the URL in the PCRE capture, and it calculates that it needs, let's say, a 50-byte memory box.
Okay, 50 bytes.
It reserves those 50 bytes on the heap. Then, Pass 2 begins. It executes the actual text replacement. However, introducing that specific, malformed question mark character tricks the regular expression engine during the second pass.
Oh, wow.
Yeah, it causes the engine to output an extra chunk of data that it entirely failed to account for during Pass 1.
So it promised to only pack 50 bytes of text, but because of the question mark, it suddenly tries to pack 60 bytes of text into a 50-byte box.
Exactly. And the software doesn't stop at the edge of the 50-byte box.
Of course not.
It just keeps writing that extra text past the boundary, dumping those extra bytes directly into whatever adjacent data structures happen to be sitting next door in the heap memory space.
And that is a classic heap buffer overflow.
Happening deep inside the XT pre-write module.
I have to play devil's advocate here regarding the auditing process because we're talking about one of the most heavily scrutinized, aggressively tested C code bases on the planet.
Oh, absolutely.
How does a memory calculation desync hide for 18 years? I mean, security researchers run automated fuzzers and memory sanitizers against Nginx constantly. Yet they all missed a memory safety bug that is trivial to trigger remotely, requires zero authentication, and needs zero user interaction. You literally just send the server a malformed URL.
It really reveals a significant blind spot in how we test software. You see, automated scanners and fuzzers are exceptionally good at finding known patterns of bad code.
Right.
But they struggle with complex logical desynchronizations spanning multiple modules, because the bug exists in the invisible translation gap between the regular expression engine calculating the size and the HTTP module executing the memory copy.
The scanners just read right past it.
Exactly. It wasn't a typo. It was a conceptual blind spot in the architecture itself.
Okay, so let's assume an attacker sends the malicious question mark, triggers the overflow, and boosts the memory box. The worker process crashes. I'm seeing arguments in some developer forums dismissing this as just a denial of service or DOS attack.
Right, I've seen those too.
The sentiment seems to be, well, the server crashes, it restarts a second later, it's not a big deal.
What's fascinating here is how dangerous that dismissal is, because it fundamentally misunderstands both modern exploitation techniques and the scale of the internet.
Yeah, it's a very narrow view.
The entire DOS-only argument relies on the presence of a defense mechanism built into modern operating systems called Address Space Layout Randomization, or ASLR.
Okay, bringing that back to the post office analogy, ASLR is like management coming in every single morning and completely randomizing the layout of the sorting room.
Exactly.
They shuffle where all the routing slips, the employee desks, and critical documents are kept.
Therefore, even if the attacker forces the system to overflow the 50-byte box, they have no idea what they are actually overwriting in that adjacent memory space.
Because it moved.
Right. They might overwrite empty space, causing a harmless crash, or they might overwrite a random variable. They cannot reliably aim the overflow to overwrite an instruction pointer and take control of the server.
So ASLR makes it incredibly difficult to turn a simple crash into remote code execution, where the attacker actually runs their own malicious commands on the machine.
Right. And on a single isolated machine, ASLR is a formidable defense. But ASLR is probabilistic. It relies on mathematical randomness, not an absolute impenetrable barrier. And this is where the sheer scale of the vulnerability comes into focus.
Because there are approximately 5.7 million internet-facing Nginx servers currently active.
Exactly. That is 5.7 million different post offices, all shuffling their sorting rooms independently.
Wow.
When you force a probabilistic event 5.7 million times, probability guarantees you will produce winners.
Of course.
Even if we assume only a tiny fraction, say, 1% of those servers happen to randomly shuffle a critical exploitable memory structure right next to our overflowing 50-byte box on the exact day an attacker sends their request.
That is 57,000 servers completely compromised.
Bypassing ASLR purely by mathematical chance.
57,000 servers falling over to remote code execution just by rolling the dice enough times. That's terrifying.
It is, and the Alma Linux maintainers address this exact complacency in their advisory. They explicitly stated, turning the heap overflow into reliable code execution is not trivial, but not easy is not impossible.
Right, not easy doesn't mean you're safe.
Security researcher Kevin Beaumont also weighed in, noting that achieving reliable, targeted remote code execution requires specific, chained configurations and for ASLR to be disabled.
Which, honestly, I want to push back on the idea that ASLR is always enabled anyway, because it is definitely not some universal standard across all hardware.
Oh, not at all.
We see ASLR turned off constantly on embedded systems. Consider the massive ecosystem of IoT devices, enterprise network appliances, load balancers, smart home hubs.
Millions of them.
Many of these physical devices run custom stripped-down Linux kernels with Nginx operating under the hood just to serve up an admin settings page to the user.
This raises an important question about resource management in hardware. Manufacturers of those embedded devices often disable ASLR entirely because randomizing memory requires extra CPU cycles and RAM.
Which they don't have to spare.
Right. On a low-power ARM processor, they prioritize stability and speed over that layer of security.
And the F5 Security Advisory confirms this exact scenario. They explicitly state that for systems running with ASLR disabled, reliable remote code execution is absolutely possible.
Yes.
The threat of an attacker taking full control of those embedded appliances is an immediate reality, not a theoretical exercise.
And that leads directly into another widespread, naive assumption circulating in the initial reactions to the briefing.
You mean the assumption about the rewrite directive itself?
Exactly.
Because a lot of people are asking, well, if this exploit requires a complex rewrite rule to trigger the memory desync, how many Nginx servers actually have rewrite rules enabled?
Right.
Is this just an obscure edge case that most system administrators don't use?
URL rewriting is the internet's traffic cop. It is the exact opposite of an edge case.
I mean, everybody uses it.
If an organization wants clean, user-friendly URLs for their marketing campaigns, they use rewrite rules. If a company needs to force all incoming HTTP traffic to automatically upgrade to a secure HTTPS connection, they use rewrite rules.
What about backend routing? Like sending traffic from an old API version to a new one?
API versioning relies heavily on it. Routing a user from V1 users to a specific backend server handling the legacy database requires a rewrite rule. Mobile device redirects, localizing content based on language headers, these all rely on the rewrite module.
Oh, it's everywhere.
If even 10% of those 5.7 million servers have a vulnerable chain configured, the attack surface remains a staggering 570,000 potential targets.
The irony embedded in that is just incredible to me. Attackers aren't targeting the core HTTP parser.
No.
They aren't exploiting the deepest foundational network routing logic of the server. They are attacking the translation layer. A configuration feature that a marketing team demanded in 2019 to make their website links look prettier for search engine optimization, well, that has transformed it into their most critical attack surface in 2026.
You are targeting the translator, not the engine. This draws a very stark comparison to a previous deep dive we did, episode 4, analyzing the Windows DNS client vulnerability.
Oh, right. But the fundamental difference there was the trust model, wasn't it? DNS is a mandatory internet protocol. It is standardized, and you have to trust it to resolve web addresses.
Nginx rewrite rules, however, are a feature. They are a tool you actively chose to configure, chain together, and enable on your public-facing edge.
You baked it in yourself.
You aren't falling victim to an unavoidable protocol flaw. You are falling victim to the complexity of your own architectural choices.
And those choices are being weaponized against organizations at a terrifying speed right now.
Yeah.
Let's trace the timeline of this disclosure, because here's where it gets really interesting. On May 12th, a proof of concept script, a PC, was published on GitHub in a repository called DepthFirstDisclosures Nginx-Rift.
Right.
The very next day, May 13th, the CVE was officially published. The National Vulnerability Database scored it an 8.1 out of 10, while Hacker News aggregators reported it as a 9.2.
Both scores represent a critical severity flaw.
Yeah, critical. That same day, F5 dropped their official advisory. By May 17th, just 5 days after the PC hit GitHub, the security firm VulnCheck confirmed active exploitation in the wild using their honeypot networks.
To understand the speed of that, we really need to look at what those honeypots actually recorded.
Right, a honeypot is a decoy server intentionally left vulnerable to monitor attacker behavior.
And VulnCheck didn't just see manual curious probing, they saw industrialized automation. Attackers weren't typing commands by hand, they had already built automated scanning scripts that grab the GitHub POSI, sweep entire blocks of IP addresses looking for the server Nginx header, and systematically fire test payloads to see if the rewrite module responds.
And once the scanner confirms the module is active, it immediately deploys the weaponized payload.
Immediately.
As of today, May 21st, that initial GitHub repository has 760 stars and 133 forks. The Python script handles all the complex math for the memory buffer padding for you. An attacker just downloads it and runs python3 posse.py-shell.
It's that simple.
The gap from a researcher publishing a theoretical memory flaw to active automated weaponization by threat actors was a mere 5 days.
5 days completely erases the standard enterprise patching window.
Yeah, it's gone.
By the time a corporate security team finishes testing the patch in their staging environment, the automated scanners have already compromised their perimeter.
Which brings me to the ultimate scenario. Let's
You're
play
told.
devil's advocate regarding the worst-case outcome here. An attacker hits the vulnerable rewrite chain, they win the ASLR probability lottery, or they find an embedded firewall appliance that has ASLR disabled. They achieve remote code execution. What do they actually gain access to?
No.
I mean, it's executing code on a web server. Why does the quote from the beginning of the briefing say they're standing in your hallway?
Because the vast majority of mainstream coverage on this bug completely misses the architectural reality of modern deployments. Describing Nginx, which holds roughly 34% of the global market share, as merely a web server, is like describing an airport's air traffic control tower as just a building with nice windows.
I love that analogy.
Yes, it can serve static web pages, but in enterprise infrastructure, Nginx is almost exclusively deployed as a reverse proxy.
Meaning it sits at the very outer edge of the network perimeter? It catches all the chaotic incoming internet traffic first?
It catches that public traffic, terminates the encrypted SSL connection, and then routes the raw requests inward. It routes to internal REST APIs. It directs traffic to private microservices running on isolated subnets.
So it's heavily connected.
It manages connection pools for internal databases, handles centralized authentication services, and bridges the gap into restricted Kubernetes clusters.
Let's visualize that breach from the attacker's perspective then. You fire the Python script, the worker process crashes, but your payload catches the execution thread.
Yeah.
You are now running arbitrary code inside that worker process.
Right.
The very first thing you do is read the Nginx configuration file. Suddenly, you see all the proxy pass directives listed in plain text. You see the internal non-routable IP addresses of the back-end databases. You see the internal host names of the employee admin panels.
You literally just downloaded a pristine map of the internal network topology.
You are no longer navigating the hardened public-facing internet. You are inside the internal network.
You are standing in the hallway, holding a map to every single room.
Wow.
Now, within the security community, there is a vocal debate about privilege regarding this specific access.
I've seen that debate.
One side argues, well, the Nginx worker process drops its privileges and runs as a restricted user, typically www data. Therefore, even if you get execution, you don't have root access to the operating system. You still need to chain a second privilege escalation exploit to do any real damage to the host machine.
Right. They're arguing that the blast radius is contained by the operating system's user permissions.
Exactly. But the other side of the debate, and this is the reality most organizations fail to grasp until it is too late, argues that root privileges on that specific Linux box are entirely unnecessary.
You don't need root, you just need reachability.
Exactly. By its very design as a reverse proxy, Nginx already possesses authenticated network access to the internal services. It is holding the trusted tokens for the entire internal network. It doesn't need to be the king of the server because it is the gatekeeper managing the trusted pathways to the internal databases.
It's the traffic cop with a master key.
Right. If we connect this to the bigger picture, we are observing a distinct structural pattern across modern vulnerabilities.
We saw it with the Windows DNS protocol collapse, and again with the Windows Mini filter driver, where endpoint detection software ironically became the primary attack surface.
And the underlying theme goes far beyond the memory management issues of C code. The structural pattern revolves around trust and network topology. The components that we treat as transparent, invisible relays, our load balancers, our firewalls, our middlemen proxies, we assume they are just dumb pipes passing data along.
But they aren't.
No, they are actually incredibly complex attack surfaces bridging two distinct sides of a network perimeter, and bridges work both ways. If an attacker controls the bridge, they control the trusted path straight into the fortress.
So what does this all mean for you listening right now? What are the immediate actionable steps to protect your infrastructure? Because hoping you don't roll snake eyes on the ASLR probability lottery is clearly not a viable defense strategy.
No, it's not. There are 4 critical steps every administrator needs to execute immediately. Number 1, rigorously audit your rewrite rules. Examine every single rewrite directive chain in your Nginx configurations.
Go through all of them.
If a rule is legacy and you do not explicitly need it, delete it. If you do need it, audit your PCRE capture patterns to ensure they are strictly validating input before processing it.
Okay, step 2. Verify that ASLR is actually enabled and functioning on your systems. Do not assume your cloud provider or hardware vendor enabled it by default.
Never assume.
On Linux distributions, you can verify this by running cat proxy kernel randomized fastbase in the terminal. That command must return the number 2. If it returns 0, you have 0 memory randomization and are highly susceptible to reliable exploitation.
Step 3 involves architectural hygiene. Segment your reverse proxy from your sensitive backends. Nginx does not need unrestricted blanket network access to every single subnet it proxies traffic toward.
Implement strict internal firewall rules.
Exactly. Implement rules between the proxy tier and the backend tier to tightly limit the blast radius. If the proxy is compromised, the attacker shouldn't automatically be able to scan the payroll database.
Finally, step 4. Patch your systems immediately. F5 has released the official fixes for the affected versions. An 18-year-old software bug does not get a pass just because it has survived in the wild this long.
And considering the Python exploits are already public, the automated scanning is only going to become more refined and aggressive in the coming weeks.
It's just going to get worse.
Yeah.
We want to thank you for joining us on this deep dive. And as you review your configuration files and patch your servers this week, we want to leave you with a final thought to mull over.
Yeah.
We have this deeply ingrained assumption in the technology industry that the older a piece of software is, the safer it inherently becomes. We assume that because code has stood the test of time, because millions of users have relied on it, well, the rough edges and critical flaws must have been sanded off years ago.
It's a very common belief.
But if an 18-year-old memory calculation flaw can sit silently in the very foundation of the modern web, only to be discovered and fully weaponized by automated scanners in 5 days flat, we have to ask ourselves, does time actually mature our digital infrastructure? Or does it merely provide a false sense of security, hiding decades-old ghosts in the code we trust the most?
Thank you for listening to Zero Day Brief.